Okay, so we want to use all these tools we've developed to solve some actual problems. And one of the fundamental questions in hydrology is, how does water evaporate from soil? And what is the rate of evaporation, and how is that related to where the water table is? So let's look at the basic problem. Let's suppose that our land surface is here. And let's suppose, maybe we can do it in blue, why not, that our water table is here. So we're going to define z equals 0 here. And our question is, how does the flux Q vary with z, for example? So in other words, if the land were deeper or less deep, how would our evaporative flux change? So we're going to assume that there's some sort of flux going up here, okay? And it's going up through the whole system and then going off into the atmosphere. And we're going to take this whole system to be steady state. Okay, so it's been going for a while, evaporation's been happening, and we want to understand what the rate of Q is relative to all these other things. So let's go ahead and say that the soil has this depth, and we'll call that L. So our distance from the water table to the land surface is going to be L. Okay, let's use Darcy's law. So what Darcy's law says is that the flux is going to be equal to the negative of the conductivity, which will be a function of either moisture content or pressure, times the gradient, and since it's a one-dimensional problem, so it's only going in the vertical direction, it's going to be the change in total potential with change in elevation. So that's Darcy's law. So let's go ahead and what can we figure out from this? Well, let's try to solve for z. Okay, so easier said than done perhaps, but let's go ahead and give it a shot. So what we're going to do is multiply both sides by dz, and well, first off, before we get too fancy, this h here. What is about this h? Well, we recall that h, the total potential, is just equal to the pressure potential plus the elevation. So we better break this up so that we can explicitly show the role of z in this whole thing. So what we're going to say then is that Q is equal to minus K, and we'll put it of H, and we'll say this is equal to the derivative with respect to z of this, which is going to be dH dz plus dz dz. Okay? I've just taken the derivative of each of these terms. Well, dz dz is clearly, that's just equal to 1. Okay? So now we have an equation which says that Q is equal to KH times this. So how are we going to solve for the dz term? We want to solve for z, okay? So let's see. We will first divide both sides by Q, by the conductivity. So we get Q over K, which is a function of H, is equal to dH dz plus 1. Okay, now it looks like and we have to be careful about our minus sign. We had a minus sign there, so we'll have to still have a minus sign. And now we can simply take 1 from both sides. So we get minus Q over K of H minus 1 equals dH dz. Now we're going to flip this whole thing, so invert both sides. You get 1 over, that's going to be minus 1, over Q over K of H plus, because of minus, that's going to be plus 1, equals dz over h over dh. And now, of course, final step, I'm going to multiply both sides by a little dh, and this will become a dh over here, and we'll get rid of the dh over here. So now we have this wonderful equation that gives us z on one side, everything in terms of h on the other side. Great. What are we going to do? Of course, we're going to integrate it. So let's integrate both sides. And we'll integrate from the water table z up to the height of the land surface L. Okay? And so we'll keep track of this. We know that by definition at the water table, little h is equal to 0, and we'll just call that up to h of L at the surface. Okay, so that's our integral. Okay, so what we have is this nice expression that relates our conductivity, pressure, and elevation. Perfect. But we haven't said anything about what type of soil we have. We have to describe the soil to be able to solve this equation. And that's where to insert our information about the soil. And in this case, what we're going to use is our Gardner conductivity. So remember 1958, he said that the conductivity as a function of h is equal to the saturated conductivity times the exponential of alpha h. Okay. This describes the whole conductivity as a function of the of pressure in that particular soil, and the soil parameters are Ks and alpha. Now, we put that in here, and if you look in the book, you'll find all the derivation and all the substitutions and changes of variables, and what we end up with is an expression that gives us, for any given elevation, what pressure you'd have for a given flux. So we say, here's the flux, here's the evaporation rate, and at some particular elevation, what will the pressure be? Or at some particular pressure, what will the elevation be? This is, in fact, the complete solution for this problem. So that's the solution. We can also put it in terms of head. So we can say, for any given flux, at any different conductivity, at any given elevation, what would the head be? So now, let's do something special. Let's say, what about Q max? What is the maximum possible flux that this soil can give rise to? Well, that would be when the pressure at the top went to minus infinity. It's pulling as hard as it possibly can. So that's going to minus infinity. This is going to minus infinity. The log of what gives minus infinity? The log of 0 gives minus infinity. So then that means that for a tension at the surface of minus infinity, this all has to be 0. And so what does that tell us? It tells us that this equals this. So we have Q over Ks equals exponential of minus alpha v, alpha z. And this will now be, by the way, we're working specifically at the surface of the soil. So that is actually going to be a very specific depth. That's going to be L. And times Q over Ks plus 1. Now you can solve this then for Q. So we can bring all our Q terms over, and we can get an expression which explicitly tells us what the flux will be when we put a totally dry surface at the surface of a system. And it'll say that's what the flux is going to be for a particular depth of water table, a particular soil type as represented by this conductivity and that alpha. So what we see then is that just using Darcy's law, we're able to solve for exactly the flux as a function of soil texture, as long as we use a very simple expression for the relationship between conductivity and pressure. And so this is showing the utility of a simple expression because it gives us very specific information, and we should label these as max, because this is only true when h is minus infinity, so that is Q max. But we get an exact expression for the flux at any given depth. And that is a very powerful result when you want to look at what the evaporation, for example, from a desert situation would be, or from any water table. And that can, for instance, give rise to salt accumulation at the surface of the soil. So this simple problem really allows solution just using Gardner conductivity and gives us a result that's very powerful.